Hi, I'm Charles Schultz of Schultz Laboratories and the Universe Science Center. One of my favorite subjects is life in the universe. Our planet is fortunate to have a very rich biosphere, as you can see behind me here. Other worlds in our solar system do have potential for supporting life, but not with the richness and diversity that we have on our world. The real search for life in the universe is actually going to go on outside our solar system, where there are many more possibilities. One of the first things we need to know is what the conditions are like in other solar systems, and that means we need to know something about the stars themselves. Let's have a look at that so we can understand what conditions are likely to be available in other solar systems.
The first thing for us to understand is that there are many different types of stars in our galaxy. Our galaxy, the Milky Way, is more or less like an island of stars in space. We know that there are somewhere between 300 and 400 billion stars in our galaxy. We don't have an exact count, of course, but that's an awfully big number. You would think that stars like our Sun are very common, but in fact they're not. If you look at the galactic population, most of the stars are red and too dim to be seen with the human eye easily. Red and orange-red stars make up something like 76% of the population of stars in our galaxy. Orange stars, which are smaller and dimmer than our Sun, make up only a few percent, and stars like our Sun around 6% or so. If 1 out of 7 stars that's red or orange supported life, then we would find just as many orange and red stars supporting life as we would yellow stars like our own. So the odds are pretty good if we start looking for orange and red-orange stars. These stars, however, have their own hazards. Small stars have less mass, smaller diameters, and put out less heat and light. Also, for red dwarf stars, which are smaller than the orange ones, they tend to be rather stormy, having a lot of flares early in their lives, so there can be hazards for planets near them.
Solar flares can be a real issue around red dwarf stars. They're not such a big problem here in the solar system. But here's the issue. Solar flares carry huge bursts of radiation. They can carry ionized particles to the atmosphere and cause lethal radiation effects on the ground for organisms. Also, they can cause immense changes in the climate. They can literally ionize the oxygen in an atmosphere into ozone, which could poison a lot of things. And electromagnetic pulse events could end up destroying any electronic or electrical devices in use on or near the planet. So solar flares are something not to be trifled with. For a red dwarf star, however, they're much worse than they would be for the following reason. A red dwarf star is much cooler than our Sun. Our Sun has a surface temperature of roughly 5,600 degrees Kelvin. For a red dwarf star, that is only 2,500 degrees Kelvin, much cooler, which means it's outputting less heat per unit area. Here's the other issue. For a smaller star, let's say half the size of our Sun, it only has 1/4 of the radiating area. So both of these effects mean that the planet must be very close to the star in order to receive the proper amount of heat and light to keep the oceans liquid. Now there's a special place, and astronomers are quite familiar with it, called the Goldilocks zone. This is a theoretical zone where around a star, a planet with a liquid ocean would be able to keep it without it boiling or freezing. So in our solar system, the Goldilocks zone extends just outside of the orbit of Venus, where it's way too hot, to just outside of the orbit of Mars. Mars is barely inside, but Earth is comfortably in the middle. If we wanted to find a planet in a red dwarf system that was in the middle of the Goldilocks zone, it would have to be seriously closer to the star because of the lower temperature and smaller size. Now the upshot is this. A planet would have to be terribly close to a red sun. This means it's going to orbit in a very short period of time compared to our year on Earth. So instead of 12 months, we're going to see a year maybe 8 or 6 or 5 or 3 months, or in some cases a couple of weeks, or even 5 days. It depends on how small the star is and how low its output is. That determines that the planet must be much, much closer and have a shorter orbital period. Now this brings to mind that there are other gravitational effects. One of them is called tidal locking. To show you an example of that, I'm going to have to show you Jupiter and its moons. Let's have a look at that. If we look at Jupiter and its moons, we discover something very interesting. A lot of people don't know this, but the moons are called tidally locked because of gravitational and tidal effects. What this means is the lopsided interior of the moon has a little bit more massive zone inside, and that tends to gravitate toward the planet, so that one face of the moon always faces Jupiter. The same thing would happen in the case of planets of red stars. Because they're so close, tidal locking will stop the rotation of the planet. At some point, one face of the planet is likely to end up facing the star permanently. Think about one part of your world having permanent noon and the other having permanent midnight. Now you can see that if this is the case, there will be the band, a sort of an equatorial band that goes north to south instead of around the middle of the planet, where the climate is fairly stable. In this zone, the sun would remain at the same height of the sky at all the times, like permanent twilight, and all of the weather would be based around this difference of temperature, from the very hot, almost desert-like noon pole to the very cold, possibly frozen midnight pole. But tidal forces can do anomalous things, and as a result, some of the planets of red dwarf suns may actually be molten from the heat. This is Jupiter, the largest planet in our solar system. You recognize it by the great red spot here. This planet has 4 very large Galilean moons. These moons are so large and so close that they're tidally locked by the planet, and they face it with the same face all the time. So this moon in particular, Io or Io as some people call it, depends on who you know, this planet or moon is actually covered with volcanic caldera. So all of these spots you see are erupting volcanoes spewing sulfur and lava into space. Now where is the heat coming from? Jupiter, as a planet, certainly is not a star, and it's not radiating that much energy. So let's talk about the heat source. So let's do a little thought experiment. Imagine a rocky planet the size of the Earth orbiting near a red dwarf. What forces does it experience? When calculating an orbit, we treat any object as a point where the center of mass of the object is. So only the center of mass is at the proper orbital speed. But the part of the planet closest to the star has a smaller, closer orbit and should move faster to stay in orbit. And it would if it were separate from the planet. And the farther face has a longer, more distant orbit, 4,000 miles farther from the star. It should move more slowly, but it's attached to the planet and being dragged along at speed. See what's happening? So there's a difference in forces on the two faces of a planet orbiting closely to a star. The farther face is moving too fast for the orbit that it would be in, and it's being flung away from the star. The inner face is moving too slow to remain in a stable orbit, and so it's feeling a drag toward the star. As a result, the two faces are being pulled apart by tidal force. Now, what do you think happens when a whole planet is being dragged face apart from the front to the back in orbit? It heats the interior by flexing the entire planet. The moons of Jupiter have internal heating as a result of exactly this effect. And a planet near a red dwarf sun, if the sun is small enough and the planet is close enough, could literally be flexed until it becomes molten. So assuming we could find a red dwarf planet that did support life, what would we see? Well, realize that the star is only the color of perhaps hot molten steel, and the light that it gives off isn't very impressive. It's mostly red and infrared. So you're not going to see blue skies. At very best, you may see greenish-gray skies with stars peering through that murky atmosphere. And not only that, on a planet that could support life, you'll discover that if it's warm enough to support temperatures that keep water liquid in the life-supporting areas of that planet, it's quite likely to be very dark. So expect really unimpressive sights. Expect a dark world, but don't be surprised to find plenty of plants and animals living there, because we've discovered even on Earth, some plants can photosynthesize infrared light, so they can work in what we would consider to be total darkness. So it's quite possible if we can get around the effect of solar flares, geological heating from gravitational flexing, and of other issues that might cause hazards to life on a red dwarf planet. We could find them to be very pleasant places to live, except for them being exceptionally dark. Get ready to bring your night vision goggles or plenty of good lighting. So that's it for our quick look at life in the universe. If you enjoyed this video and would like to see more content like this, please subscribe to our channel and visit us at schultzlaboratories.com and universesciencecenter.com.
I'm Charles Schultz of Schultz Laboratories. Thank you for watching.